Hello, welcome back to Larry's classroom. Today we're going to talk about how we can use our simple meter movement that we've talked about in the last couple lectures to make an ohm meter. Well, what does an ohm meter consist of? We basically have our meter movement. I'll just draw a picture of a meter here. And we have, this is going to be a 1 milliamp meter movement with a resistance to the meter equal to 50 ohms. Our current of our meter is 1 milliamp. We want this, with a short circuit, we want this meter to read full scale. We're going to have a 1.5 volt battery in series with the meter. And there's our negative and positive terminals of our meter. We have a resistor, and we have leads coming out of it. Now, to get 1 milliamp, we need a total resistance. Remember, we have R equals V over I, and that with a short circuit, we want this meter to read full scale. Well, if we have 1.5 volts and 1 milliamp, which is 0.001 amps, 0.001 amps, we do the division here. We need a total resistance of 1500 ohms, 1500 ohms. Well, that will be RT, so RT equals 1500 ohms. But RT is equal to, we're going to call this R1 here, is equal to Rm, the resistance of the meter, plus R1. Well, we know that we need a total resistance in this circuit for a short circuit to give us 1 milliamp, which causes the meter to read full scale, because it's a 1 milliamp meter movement. So 1500 ohms is equal to Rm, which is 50 ohms, plus R1. Well, we solve for R1, subtract 50 from both sides, we end up with 1,450 ohms for R1. So we're going to put that up here, 1,450 ohms. 1,450 ohms. And an analog ohm meter, like we're talking about here, when you put zero resistance, if you take your two leads and touch them together, the meter will read full scale, 100%. So that will be calibrated as zero ohms. If you put a high resistance in here, you have lesser current through your circuit here, so you have lesser deflection of the meter. So on the ohm meter, we have low resistance over to the right, high resistance is over to the left. And let's look a little bit more. I'm going to go ahead and erase this stuff. I'll leave the Ohm's law up here. But let's do some examples of how this works out. We have a total resistance of 1500 ohms. Well, we're going to do some calculation. We call whatever resistor we're measured out here, we'll call that R external. The resistance that we're measuring. And RT now remember before we had RT was equal to the resistance of the meter and the resistance of the R1 here, but we also had 0 ohms. So RT really is equal to resistance of the meter plus R1 plus RE. Now when we shorted the leads together, RE was 0, so we just had the resistance of the meter plus the resistance 1, which is in series with the meter. And I'm going to draw a little dotted line around here, which would basically represent, if you're using your ohm meter, would represent the case of the meter. This stuff would be inside the meter. This resistor is inside the meter. Of course, the meter movement itself would be mounted on the face of the meter. But these would be where your test leads come out. I'm going to draw some red circles here. That's where your test leads come out of the meter. And you can use them to connect to any resistance you desire to measure. So we're going to do some calculation and think about how this meter works. I'm going to put here resistance external, which is the resistance you are measuring. Resistance total, which is basically going to be Rm, the resistance of the meter, plus R1 plus resistance external, and that's our formula we have over here. The current, this will be the current that's actually going through the circuit and which is causing the meter movement to move. And I'm going to put percent scale. So that's going to indicate where the meter needle sets while you're making this measurement. I'm going to draw over here a bigger scale of them, just a bigger picture of a meter that we're going to make some marks on as we do this. So when we started out, we already did the first one. Resistance external was 0 ohms. Resistance total was 1450 plus the 50 ohms of the meter movement, which is 1500 ohms. And our current, we got our current formula. I equals V divided by R. So here we used 1.5 volts divided by the total of 1500 ohms in the circuit, and we ended up with 1 milliamp, which is also 0.001 amps. And that was the movement, the current rating of the movement of our meter. We know that that's going to push the meter up to full scale. So we're going to over here have at full scale, we're going to have a mark that says 0. So that'll be 0 ohms. So now let's put a 500 ohm here. R equals 500. So we're going to do 500 ohms. Now our total is now going to be the 1500 ohms that's inside here. We're going to write that right here, that Rm plus R1 equals 1500 ohms, because we're going to use that number several times. 1450 ohms for R1 plus 50 ohms for the meter movement, 1500 ohms total. So our total is going to be this 500 plus that 1500. So it's going to be 2000 ohms. And now if we want to figure out the current to the meter, we have 1.5 volts divided by 2000 ohms, and we end up there with 3/4 of a milliamp when we do that calculation. So that gives us a 3/4 scale deflection, right? So right about here we're going to have another mark. And this is going to be 500 ohms, because that's how far our needle will deflect if we have 500 ohms. So we're going to put 500 right here. Now we're going to try another resistor slightly bigger. We're going to go to a 1500 ohm resistor for our external. And we're going to change that value to 1500 here. Well, what is our R total? It's 1500 plus this 1500, so we end up with 3000 ohms here total. And when we do the calculation of the 1.5 volts, I didn't draw this circuit right. I see I got this thing coming down the wrong place. I apologize for that. Yeah. The power supply has to be in series with the meter, not... Yeah, so we get our current flow this way through the whole circuit. Anyway, now we have 1500 ohms plus RT of 1500 ohms gives us 3000 ohms. We do the calculation again, 1.5 volts that we have right here, divided by 3000 ohms. And that ends up equal to be, that ends up being half a milliamp. And let's fill this in here to full scale deflection, then we had 100% here. Our 3/4 scale deflection with the 500 ohm resistor, we had 75%. And we're drawing those numbers up there too. With our 1500 ohms, we have half a milliamp, which is half of the 1 milliamp that the meter's rated at. So we end up with 50% meter deflection. So right in the middle here, we'll make another mark on the face of our meter, and that will be labeled 1500. I'm going to leave the comma off of there just because it's kind of cluttering things up a little bit. You know the 1500 should have a comma in it. So we got half scale, and you notice that this 1500 ohms that we're reading for our external is also equal to the internal resistance of the meter with the meter and the R1 in series. And it makes sense that the 1500 alone would give you full scale 1 milliamp. If we go to twice as much resistance, we're going to get half as much current, or half scale. So basically with this type of a meter, the resistance right in the middle of the scale is going to be equal to the resistance internal to the meter. Now we're going to do another one, 4500 ohms. And what is 4500 for our total? We want the resistance of the meter plus the resistance R1, which was 1500 ohms, plus the R external, got 4500 on there. And that gets us up to 6000 ohms. And if you did the calculation, 1.5 volts divided by 6000 ohms, we'd end up with 1/4 of a milliamp of current in the circuit. 1/4 of a milliamp causing the needle to swing to one point or the other. And that is 25%. So we're going to put right here 6,000. There's basically 25%. Let's move that over just a little bit. 25%, 50%, 75%, 100% of the range of the meter movement. If we have 100,000 ohms here, we end up with 101,500 ohms total when we add the 1500 to the 100,000. And I'm not going to bother to write the formula. It'd be 1.5 divided by 1,105, but it's going to clutter things up a little bit. That would give us a current. That gives a current of 0.15 milliamps. Which is about 1/68 of a milliamp, so we'll put the fraction there. And we'll put that, that's going to be, well, that's going to be about a 1/10 of a percent or something. It's going to be way over here, almost nothing movement. So we're going to put down 100,000 right there. So when we do the leads together, we got a needle right there. We put 500 ohms in here. Let's put the 100,000 ohms here too. That was our last calculation for our last line of our table, and this is like less than 1%. It's almost nothing. No, that's about. That's about 15%, isn't it? Yeah, it's about 15%. Yeah, that's about 15%. So get that here roughly at the 15% place. Then when we put the 1500 ohm, and you notice this is, we move from here to here, 1/4 of the range of the meter, with a change of 500 ohms. Now when we go to the 1500 ohms, we end up here half scale. When we went from 500 to 1500, we went from 75% to half to 50%. So it took 1,000 ohms increase to go that. 500 ohms increase to go the first quarter down scale. 1,000 ohms increase to go the next quarter down scale. And here it's going to take 4,500 ohms to go the next quarter scale down. If you look at the 6,000 ohm, we're about 25%. If your needle is right there. And now when we go to the next 25% for the or it's not 25%, another 10% or so actually. We go from 25% to 15%. That's the 100,000. So it took 96,000 ohms of increase in resistance to move that last quarter. So you see this scale is not linear. In other words, it doesn't change in direct proportion to the resistance change. Basically, as the resistance increases and you go down scale, they get closer and closer together. Which means you can read resistances in the 6,000 to 500 ohm range better than the ones in the 6,000 onto infinity. Now any ohm meter of this type with 0 ohms, the needle will go all the way to the right full scale. So it's always 0 full scale. And when you open the leads, and there's no current, over here on the, we have infinity. So always on this type of meter, on the left side of the meter, it's infinity. On the right side of the meter, it is 0 ohms. And the resistance divisions get closer and closer and closer together as we increase the resistance and move down scale to the left. And that is because current is equal to voltage over resistance, And the voltage we're holding constant is we're increasing the resistance, and that graphs out with a graph that looks kind of like this. It doesn't go down linearly, it decreases faster, and it levels off, slower and slower. And that the fact that it's leveling off is what's squeezing these marks together on the left-hand side for the higher resistances. And we're going to talk a little bit about a multi-range ohm meter, how that works. We're going to erase this stuff here, these calculations. You've seen them now. You've seen the nonlinearity. You've seen how the resistance values get closer and closer together as you get higher resistances and the meter moves downscale to the left. Erase some of that. And now we're going to draw a picture of a more common meter circuit that allows you to change ranges. You can see that that one we just do worked pretty good in the 6,000 to 500 ohm range, get reasonable estimates. But if we're trying to measure just a few ohms, we end up way near the right scale. If we're trying to measure hundreds of thousands ohm, we end up near the left scale. So you need different ranges in that sort of a meter. So we're going to just put a box here to represent a meter, and we're going to say that this is a 50 microamp meter. And let's see, 50 microamps. We're going to use 1.5 volts again. Yeah, we're going to need a total resistance with 1.5 volts of about 30,000 ohms in this meter circuit to get full scale deflection with 0 ohms when it's shorted together. Well, when you draw a real meter, an actual, you got R. I'll call this R adjust. You got a little adjustable potentiometer type resistor, and then you have your R1. We're going to run this one on 1.5 volts, just like we did before. We have a R shunt here. I'm going to spell the word. R shunt, which goes in shunt with the meter. We have our 1.5 volt battery like we did before. You can run these on different voltages. We're just using 1.5 for our lecture example here. 1.5 volts. And it goes out to your meter leads. And I'll draw some nice little red circles again where the meter leads connect up. We're not going to get so involved in that on this part of it. When you operate a meter like this, you select your range, which selects your shunt resistor value, and then you always, with the ohm meter, you short the leads together and adjust this R adjust to get a full scale reading. But what happens here for now we'll just say this R shunt is 10 ohms. We got our R1 plus R adjust plus RM, the resistance of the movement, going to have to be about 30,000 ohms is going to have to be. For R, I'm going to call it R internal. Now it's the resistance in this top branch here. And we did that by going, we used this R equals VI, so we had the 1.5 volts and the 50 times 10 to the minus 6, which represents the 50 microamps, and we ended up with 30,000 ohms. This is a more sensitive meter than we used in our last example. Is a 50 microamp meter, and RM is probably going to be about 2,000 ohms. And R1 is probably going to be, say, 25,000 ohms. So you would, when you set it to 0, you're adjusting this R adjust to get about 3,000 ohms. 25 plus 3,000 plus 2,000 gives us the 30,000 we need for full scale deflection of our meter movement. When we design a meter like that, when we short this together, we get our 30,000 ohms through here, our 50 microamps through this circuit, and we get some current through our shunt, which we could do the calculation, but I guess it would be 1.5 divided by 10. It would be about 150 milliamps. 1.5 divided by 10 is 0.15, or 150 milliamps. Now, if we put a 10 ohm resistor out here, well, why don't I draw a resistor? Yeah, let's make a prettier looking one than that. When we adjusted it with this shorted, what happens now? We didn't change that. We have the same 1.5 volts from here to here, but the current going through here and the current going through here ends up half of the current is diverted. So now we still have, we end up with half as much current through our meter, and we end up roughly at half scale. So we change the range of our meter by changing our shunt. We could go to 100 ohms. And now it's going to take roughly 100 ohms here to get the half scale reading, because the current, this is a high enough impedance with 30,000 ohms that not much current goes through here, so we're mostly reading the voltage across that 100 ohm resistor. We half the resistance, we half the voltage, we end up at about half scale. So we change ranges by putting different shunt values in. And the bigger the shunt value, the greater the range. And the range, it ends up mostly set in the middle value, and that's kind of where we want to operate when we're reading this kind of a meter. No matter what range we're on, when we short the leads together and adjust this to 0, shorted leads always reads full right scale equals 0 ohms. Full deflection equals 0 ohms. Always. No matter what range we're on. And no deflection equals infinite ohms, or an open circuit. And I think you can see as we make bigger and bigger resistors, it would take a bigger and bigger resistor here to read half scale. So we change our value of our meters that way. And when you work with a real meter, you're going to see a switch on the front, which is probably going to say something like R times 1, R times 10, R times 1,000. So I'm going to erase this circuit that I drew, and I'm going to draw a picture of a meter scale. We're going to talk about that a little bit. So the meter scale, always 0 way over here. Always infinity way over here. And I'm only going to put the middle value in here for now, but let's just say that we have 10 here in the middle. When the needle's facing there, that would say 10 ohms if we had R times 1. If we were on R times 1 scale, that would be 10 ohms. But if we set it to the R times 2, or R times 10, you're not going to see an R times 2. Now that 10 represents 100 ohms. If we have a R times 1000 range on our meter, that middle scale, that 10 is 1,000 times 10, that's 10,000 ohms. And we'll say that your meter has an R times 10,000 to it. It varies on what the manufacturer decided to use, but 10,000 times 10, that'd be 100,000 ohms at center scale. So what do we see here? We have on the R times 1, 0 to 10 ohms represents the top half of the meter movement. R times 10, 0 to 100 ohms represents the top half of the meter movement. R times 1,000, 0 to 1,000 ohms, or 0 to 10,000 ohms will represent this portion of the meter movement. R times 10,000, 0 to 100,000 ohms will represent this portion of the meter movement. And we're changing that R shunt to bigger and bigger values as we go down here. It allows us to make this meter work for higher resistances. Well, let's think about one of a common usage. Well, common usage for an ohm meter is simply to test the resistance of a resistor or some component part. And when you're doing ohm meter checks, the ohm meter, as you recall just a minute ago, has its own power source. So you do ohm meter checks with no power on the circuit. And a lot of times to get a good check, we have to actually take a component, disconnect one end of a component because there are other components in parallel, and we've talked about parallel resistances, and you know how that changes the resistance. If you had inside a circuit a 1500 ohm resistor and you want to know if it was correct, and you just put your meter across it, maybe you read 200 ohms, but maybe there's a 150 ohm resistor somewhere in parallel. You disconnect one end, you read it, now you know the value of that resistor. So your certainty of doing a good job of getting a good reading kind of requires that you have no other things connected, at least one end free. So another thing besides just reading a resistance, ohm meter makes a good continuity check. A wire normally has, for all practical purposes, zero resistance. So if we got a wire here, I'll go ahead and draw a meter. And we got leads coming. Let's use a different color for the lead. How about that? We'll use this red for the lead. If I hook one end of the meters, one lead of the meter to that wire, and the other lead to the other end, we're going to basically get a full scale deflection, because that represents, for all practical purposes, zero resistance. I mean, it's not zero, but it's very, very low. We disconnect it, the meter goes back to the left. So if we've touched our leads together, we've zeroed the meter, we know our leads work, we know our meter's got a good battery, we know it's calibrated, 0 ohms is up on the far right hand, full deflection of the meter movement. If we put our leads on one end, both ends of opposite ends of a piece of wire, and we see this, what's that tell us? That somewhere in here that wire's got a break in it. And that can be a useful thing to do when you're troubleshooting a circuit. You know, if you think something don't work, I got power here, got power, no power there, I shut things down, say, oh, I've got a bad wire here. Maybe you got to put a new wire or whatever. So when you're checking continuity, we call this continuity, making sure the wire is continuous, has continuity. When you see 0 ohms way over here to the right, that's a good indication. When you see infinite ohms over here to the left, that's an indication that it's bad. Let's think of a case we might make use of this. Suppose we got a cable, bunch of wires. I'm just going to draw 4 or 5 wires coming out of there. And we got 4 or 5 wires coming out of here. And we've got a terminal block. Bunch of terminals on it. And we see this wire connects to that terminal. We don't have any markings to tell us which wire that is over there. Well, how would we deal with that with our using the ohm meter as a continuity check? Well, we take this, put one lead right on the terminal where the wire we're trying to locate is attached. We'll take the other lead and we'll hook it to each one successively until we find the one where the needle swings full scale. Let's say we found that one. Now we know that this wire here is that wire there. So we've identified a wire. And it can be quite useful, you know, if you don't have markings or you have a cable with same color of wires. Now let's think about another case where you're doing something similar. Maybe you got a two-wire cable that goes from one cabinet to another cabinet that's maybe it's 100 feet away. How are you going to do that? You want to see if this cable's good. Well, you can go over here and you can apply a short to that far end of the cable, then hook your meter up to here and to here, and if both of those wires are good, you'll see that needle swing to the right full scale. That tells you got a good, that both of those wires are good in that 2-wire cable. Well, let's think a couple things of what are valuable, what you can do with a common use of using a meter as a continuity detector. Well, you recall maybe before that we represented a heating element as a resistor, but it's a low value resistor because we want to draw a lot of current and make a lot of heat. We can take our meter and we can measure that. Say your coffee pot won't heat up. Maybe you put your meter on there and you read an ohm and a half. Well, ohm and a half on 120 volts is going to be a little less than an amp. An amp times 120 volts would be 120 watts. That's probably kind of low. Maybe you'll read a half an amp. Probably read more like a half an amp. So you end up with half an ohm, I mean. Yeah, that would be too much, I think. Anyway, it's going to be fairly low. Let's see what happens if it was 10 ohms. 120 volts divided by 10 ohms gives us 1.2 amps. And for power, remember power is equal to volts times amps. So we got 120 volts times 1.2 amps. What do we end up with there? 120 and about another 20. We get about 140 watts, I guess. Yeah. And that was if we measured 10 ohms. If we measured 2 ohms, let's say we measured 4. Yeah, 20 and 10 was. Oh, this was 12. This was 12 amps. That's why it don't seem right. 10 ohms, 12 amps, and 120 times 12. That's more like 1,400 watts. That's probably a little more power than the typical coffee pot. But let's say we had 20 ohms there. That would give us the 6 amps, and 6 times 120. That gives about 720 watts, which is probably not an out of ballpark figure for the for the resistance of the heating element in the coffee pot. But another thing I got to point out, that's after it's heated up. Typically these resistance of these elements will be quite a bit less when they're cold, and as they heat up, the resistance goes up and the current drops off. So really, maybe you need 20 ohms when it's hot, but you might only have 5 ohms when it's cold. So when you're reading the resistance across a heating element, you expect to have pretty low resistances. And it is very easily to know that this is the whatever it is when it's cold on most things. There's some things that are different, but typical heating element's not going to be so. This would be your maximum current and your maximum wattage. So you can figure that when you put the power to it, it'll warm up, the current and wattage will drop off. So you can do a quick calculation on this, and that would be your maximum wattage. And if you're looking at a heating element for say a coffee pot or even a toaster, and you end up with a maximum wattage of 5 watts, okay, your resistance is too high. You have what we call an open heating element. You're never going to get your coffee hot or your toast toasted with only 5 watts of power. So continuity, good check on wires. We talked about that. Good check on heating elements. You want to have low values, very close to 0 for wires, and in the range of probably most time only a few ohms when you're measuring a heating element. And the same is kind of true. We looked at, I think we looked a little bit at a light bulb. We had a circuit like this, or a symbol like this with a circle around it. Well, that there's like a wire inside that gets hot when you draw current. You're called your filament. Filament. That should be low resistance. If you were wondering if the light bulb was bad, you can check it with your Ohm meter. If you didn't get low resistance, you know that light bulb's no good. Fuses go in line with wires and kind of take the place of the wires. They pretty much near 0 resistance, and if a fuse is burned out or blowing, we're going to see near infinite resistance in it. The winding of a transformer is typically pretty low resistance. That's just a coil of wire. Same thing with the windings of a motor. If you're wondering about a motor and you start checking on the leads and you don't read no current through one of the windings, that motor is probably burned out, and you might be able to smell it on a motor too. But the Ohm meter check is a little bit more definitive. A solenoid that operates a little slug magnetically to open a latch or open a valve, same thing. It's a coil of wire, should be low. If you put your meter across that and you find you're way over here near the left side, it's probably bad. But if it's up in the half scale or 75% scale, depending on the situation, it's likely is a good unit. We've been doing a lot of problems on the board. I would advise you to look for a book and try to do some problems on your own, or if you can't do that, maybe look at the ones we did on the board, maybe rewind, stop the camera, write them down, see if you can work it out on paper. And if you get a little lost, watch a little further and see what the procedure was. And doing this kind of work, exercising your skills, will be of value on getting better and better at understanding electricity and analyzing electric circuits and such. Anyway, appreciate you coming back. Be sure to like and subscribe. And until the next time, keep on learning.